design, VLSI design, quantum computing, cybersecurity, and computer vision. He has published around 130 research papers in referred journals and conferences. So, let's welcome him. So, our main speaker today is Dr. Kenneth Regan. So, Dr. Kenneth Regan has worked on the computational complexity, which is very much like a computer theory topic. So he'll not talk on that a lot today, but rather he would talk about something different. Anyway, he has done his BA in 1981, before I actually was born, from Princeton University, and then he has done his doctorate in 1986 from Oxford. Later, he was the postdoc at Oxford and Cornell, and from that time onwards, after that, he joined the University at Buffalo Computer Science Department. So today's talk also is talk would be on the chess cheating. So first of all, he's an international master in chess, and he has a very good research program on chess. What he does is it does the predictive analytics, and it finds out the cheaters, chess cheating. So chess cheating is a different word, a different thing altogether. Chess.
Thank you, yes.
So we'll come to know more about that thing. So he is also the Fair Play. He is also advises the Fair Play Commission of the World Chess Federation, and he is actually has created that the Fair Play Commission in 2014. So I'll just show you one image of him before we go further.
Oh, yes. Yes.
Catching chess cheaters. So today's topic would be mainly on that.
Of chess.
What?
If you miss the cheating, I said, chess cheaters can Regan.
Well, yeah, that's true. No. Well, yes, if I can, yes.
So without further delay, let's start and thank him first.
Okay. Yep. Thank you very much. Yep. Okay.
So we are very happy to. Is this working? We are extremely happy that you could find time, thanks to Amlan. He is very keen.
That's right.
Yeah. He is very keen to bring you here, and we gave him hot khichdi, which is the patent of West Bengal.
Okay, it was very good.
So
A good revival.
I'm sorry we got slightly delayed for various reasons. We welcome him, and before we begin, we'll, as a token of appreciation, we'll give him a memento. Bring the books. So this lot contains 3 books. 2 of them are written by the famous Nobel laureate Romerola, Life of Ramakrishna and Life of Swami Vivekananda. The other one is selections from the complete works of Swami Vivekananda for him to read. I hope he will enjoy reading these books.
Okay. Thank you very much. Okay, thank you very much. I have tried to follow wise words all my life, and on my previous visit to Kolkata, I spent an enjoyable, complete day at the Rabindranath Tagore Museum.
So we have a small gift for Professor Amlan Chakravarti also. This is in Bengali. This is Swami Vivekananda Patravali. So over to catching chess cheaters.
Yes, well, actually, trying to catch more than chess cheaters, trying to catch the flow of our mind when we are not, and hopefully not, cheating, but certainly when we are concentrating very hard. Okay, now let me see, how do I, I'm tapping on here, using the mouse. Okay, I see. Okay, great. So, actually, let me Just, actually, let me do a real test. I'm just curious about this. Okay. I compete with the president and with Shakespeare, but I think I'm somewhere down here. No, not on the first page. Not in Calcutta. Okay. Brian Regan is a famous comedian. The course that I am teaching comes up, but this is my current course teaching this term, which I am not doing. My current doctoral student is giving my lecture later today. This is my main page, and it has a link to the chess research site, a link to the talks, has a link to the Gödel's Lost Letter blog, which I may show something from toward the end of my talk, and the current item is in fact part of this talk. So this is a blog that I share with Professor Richard Lipton, with whom I've also co-authored this textbook on quantum computation. I have other things, personal things on this page as well, some of my creative writing, my wife and 2 children, who Tamal we've been very happy to know Tamal at the time this has come up. Okay, but, so here are my talks. They're all here what you can see, and this is the talk that I am giving today. I have a no-pause version of it that's easy to read, but I will be presenting the version that has the pauses. So anyway, this is my wife and 2 children from Nichols School. Okay, so what laws act on the mind? Okay, an attempt to take a path of discovery, which Bhattacharya Tamal has accompanied me for the majority of the years that this has been done, since the year 2011. Okay, so, okay, so let's see, how do I, okay, I do it this way. And let's see, page down. Okay. Now let's see, just what's these? Okay, great. Okay, so competitive chess, concentrating the mind. The popularity of chess has been growing, despite the fact that the computer defeated the human champion Garry Kasparov now 22 years ago, before many of you were born. Okay, so, I just, I did some, what did I touched the space bar. Okay, that's what I'm looking to do. Okay, great. Now, as an example of that, India now has 59 grandmasters, including a 12-year-old named Gukesh, who just obtained the title. Well, that's 59 grandmasters more than India had when I began playing. In fact, Anand, the world champion, was the first Indian grandmaster 31 years ago. And in fact, 35 years ago, I was as highly rated as Manuel Aaron, who was India's highest rated player. So nowhere near that now, of course. But Bangladesh has 5 grandmasters, and more to note, I've been following international chess for 10 years, and Bangladesh, not only the main championship, but team championships and youth championships are now carried on the major compilations of chess activity. Okay, so Dhaka has arrived as a capital of the chess world. Okay, many schools have programs in chess. In fact, it's taught throughout the countries of Armenia and Azerbaijan. And one thing that's helped me is that many more games by players of all strengths have been preserved. So one of the neat things about chess is you can get the exact record of a game has been played, relive, and examine the decisions that people made. The same way one can do with a cricket match if one has the ball-by-ball record and video evidence and decide, well, should they have set a less attacking field or a more attacking field at a given stage of a match. Well, we can do the same in chess. Okay? Now, so in the past year, as part of my vocation with checking for possible incidents of cheating and also simply as research, I took data from more than 58,000 players in tournaments over calendar year 2018, almost 250,000 games, and most importantly, over 10 million positions in those games, which I sent through computer analysis using our Center for Computational Research supercluster on the university. And
How do you define cheating in chess?
well, we'll go through the idea of how my model does that. But the main thing is I take a lot of data. And the most important thing for me to have is all the data from non-cheating players so that I can tell the difference. And it is the pattern of human thought and how that is reflected in data that is the main subject of this talk. Okay. All right, so now the first important thing to know about chess players is everyone has a number. That number is the rating of the player on a numerical scale that was invented almost 70 years ago. And the mathematical point of the scale is that the number, the rating number, should correspond to a forecast of the likely score of players who are facing off in a match. In the recent World Championship match, Magnus Carlsen and his American challenger Fabiano Caruana were within 3 rating points of each other, very close. So that predicted a 50-50 outcome, and indeed all 12 of the initial games were drawn until a faster playoff resulted in a defense of his title for Carlsen. So the idea is the forecast should depend only on the difference in ratings. So if the difference is 0, like in the World Championship match, then 50-50. If the difference goes to infinity, then the stronger player's chances approach 100%. And to set the scale, the people who designed the chess system decided that 200 points should be close to 75% expectation. And they also had the idea, if a chess game really is like a 50-50 coin flip, the standard deviation of flipping a coin is 1/4. Okay, so 1/4 up or down of series of coin flips. So that was the idea, that 75% expectation, 200 rating points should be one standard deviation of performance. Okay, and when you have something mathematically that stays in the bounds 0 to 1, while its argument can go from 0 to infinity, or to negative infinity if you are lower rated, then chances are you have something of an S-curve. And the simplest natural S-curve is the logistic curve, and this is in fact the exact logistic curve used by the United States rating system. So there's the delta, and the E is the expectation for the stronger player. So that if delta is 0, then it's 1/1 plus 1 is 1/2. If delta goes to plus infinity, it goes to 1/1, because the minus in the exponent will make it go to 0, and so on. Okay? And then the way the rating system works is the formula sets your expectation. If you actually do better, then your rating goes up. If you do worse, your rating goes down. And they're trying to adjust your rating so that further forecasts using these formulas will be spot on. And now this idea is used not only in chess, it is used in major sports. I mean, squash, international squash, was one of the first sports besides chess to adopt it. The statistical website 538.com uses it to set betting lines and forecasts for National Football League teams and baseball teams and basketball teams. Okay, so it's very much entered the mainstream, and yet it's a very simple formula. So here are some examples in chess. So Bobby Fischer hit 2,800 on the ELO scale, didn't quite make that on the international scale, whereas the current world champion Carlsen was the first to go well above 2850. So the highest human rating all time is 2882 by Carlson 4 years ago. Computers, however, though, are now rated 3300 plus, which means that they are more than 2 standard deviations above humans in quality. Okay, and they're going to take a lot more than 75% from us. Okay, this is approaching perfection. And there are now 42 players rated above 2700, not very many. The number 100 player in the world is just above 2650. When I started playing 40 years ago, my 2450 rating placed me in the world's top 400. But now I'm about 3,000th in the world with the same rating. Then that's still above Master. Master is 2,200. I'm an international master, about 2,400. Grandmaster starts really at 2,500, although the titles are different from the ratings. Then as you go below, you get to various amateur class designations, down to an international floor of 1,000, which is a bright beginner. So if you've played just a few chess games and started entering tournaments, you're adult beginners, that's probably where you would be. And as you see from this curve, the majority of people who play online, another arena where chess has greatly grown in population, have ratings that peak about the 1,000 mark. It's amateur players who love chess, just like amateur players love football or love cricket, even though we talk about the masters, the Messis, the Ronaldos, and the Sehwags and Sachins. Okay, so now, now one of the purposes of my model is to compute ratings a different way, not by the results of the game and that formula, but rather by analyzing the objective quality of your moves as judged by those 3,300 rated computer programs, whose judgment is so strong that we mere humans, 500 and more points lower, don't have any reason to differ from their verdicts on the numbers. So those chess programs are authoritative for us. And what the programs give is they give values in units of hundredths of a pawn. Okay? And the idea of their values starts very simply with the values of the chess pieces, as quite a few of you may have seen it in books. So the name chess, by the way, comes from chaturanga or shatranj, meaning 4 sides or 4 wings or 4 strains of the army. The idea of the diversity of different ranks of society and military training combining to form a military force. So there are the pawns, the foot soldiers. They're 1 pawn each, or 100 center pawns. Now I'm going to group the knight and bishop together in the 300 to 350 range. Then the rook, we all agree it's 500. And the queen, which used to be a much weaker piece called the vizier, the wazir, the advisor, now a major component worth 900 to 1,000. And then computer programs employ many other numerical measures of position structure. So my model takes those values and produces forecasts and measures of skill from the measured change in value of the moves that you make. And one virtue of this is a typical top player may play only 100 games per year or even less, and that's not very many statistical data points. But those 100 games will comprise over 3,000 moves, and that's a very nice data set. Okay? Now I'm going to discuss the ratings a bit later. I'm going to focus instead on the notion of value that we have. And we want to translate from value to an expectation. What is your chance of winning the game? Or if you had a position of this value 100 times, how many points would you expect to score? All other things being equal, in particular your opponent being as good as you are. Okay, so it's given by this formula, and that should look familiar. It's another logistic formula. And it has the idea that if the value is 0, meaning there's no net profit to you, it is an even game, your chances should be 50%. As the value approaches infinity, your chance in the game approaches 100%. And if it's somewhere in the middle, well, in the middle, I'm going to put both the b and the v to be 1. Then it's, well, not quite 75%. 73% is what you get. Okay. In any case, this describes another logistical curve. Okay. So one logistical curve was giving the forecast between two players. This is giving your forecast in the game based on your value. There's a slight refinement. We're going to include a chance that regardless of your value, you make a completely silly mistake and blow the game, even if you're far ahead. So it's a slightly adjusted logistic curve called a Richards curve. So here is an example of the points to expectation curve. And the fit line is this little green line that you can't see, and it stays a little above 0 because of that A. So this is actual data from over 100,000 moves played by players of 2,000 rating. And so the actual data conforms very closely to the predicted logistic curve. So this is clearly a law of expectation in terms of the position value that is obeyed by chess computers and reflected in the human population by the frequency with which players of a given value go on to win their games. So if they are up 1 pawn, they win the game about 70% of the time. Okay. Now, the slope is the b of this, and this does change as your skill level changes. So on the left is a lesser slope than the world's best players, shown on the right, which means that if you have a small advantage, even against an equal opponent, the world's best players are more likely to convert it into a victory. Okay. So, and it turns out that that slope varies linearly with rating R, and it is therefore also a measure of skill. Okay, so now, you may have heard about Google DeepMind's AlphaZero program, which taught itself to play chess and previously Go from scratch. Okay, and it bypasses the notion of value, using only the expectation as estimated by the frequency with which it beat itself from a position. And it does not have the problem of slope, because in training by self-play, it's always referring to its own expectations. So it ramps up its own slope as it trains itself. And in that way, it does not have to use a notion of value. It goes directly to the expectation. But I, in my anti-cheating task, I have to rate the likelihoods of real flesh and blood human players of all ratings, so I have to be concerned with all of the ranges of this scale. And part of the problem is that if I'm given games by a player, I have to judge the rating in order to set some of the parameters of my model in order to judge the rating. And I run a risk of circularity, which I call the sliding scale problem. So AlphaZero doesn't have to deal with it, but I do. Okay? Yes?
At what stage in the game do you evaluate the points before deciding?
Now, I skip turns 1 to 8 because those are too early in the opening to really make a judgment. So I begin at turn 9. And when I'm testing someone for cheating, I also eliminate all positions that are already recorded in books. But otherwise, yeah, I use the computer's verdict on all the relevant positions in the game until one player is really too far ahead. Okay. Now.
Why did you select 8?
So this same choice was made in international computer competitions as to how much of the opening they set before they allow the programs to play their own moves. And it's just my feeling, there are some chess openings where I would go earlier and many where I would go later, but it seems to be the golden mean of where the computer value takes over from fashion and strategy as being a measure of goodness of the move. So it's a somewhat arbitrary choice, but others had made it before I did. So that's a great question. And you're going to see something that's going to tell you how important that arbitrary choice is very shortly. Okay, but now I showed you two logistic curves, and both curves had a factor in the exponent. And the same factor is mediating both the scale of whether you count a queen as 900 or 1000 or 1000. If you change the scale, then you have to change the factor of B. But the factor of B is tied to skill at chess, and they are the same thing. And what that means is that skill at chess is primarily the scale and vividness of one's perceptions of value. Okay. And there's also the other quantity, A, that also varies with rating as one would expect. Lower rated players make more large mistakes. Now, I'll pose to you a question. Given a value of a position, the computer says the position has a given value V, say you are 1 pawn ahead. Would you rather it's your turn to move or the opponent's turn to move? How many would rather have it be your turn to move? I think some of you are skeptical. How many would rather it be the opponent's turn to move? Okay, I see. All right. So cannot fool anyone. Well, here is actual data. It's a kind of Murphy's Law. What the data shows is that if it's your turn to move, that's the lighter purple line that's slightly lower by 2% in expectation across the board. If it's your turn to move, it means that you have the first chance to make a game-losing blunder. If it's the opponent's turn to move, that chance is on the opponent first. And it makes that much of a difference in the expectation. When we got these results in a 3-person paper that Brother Bhattacharya Tamal was involved in, I thought this was a mistake. But it's actually just a law of human existence, the same as Murphy's Law, that things go bad before they go good, sometimes. Okay, now, however, though, there is a more positive law that's involved here. And it's a question of how sensitive are we to difference in value. Now, even if you know chess, you might think, my goodness, it's measured down to differences of 1/100th of a pawn or 2/100ths of a pawn. Could I really tell such differences in value? Well, in the math, the answer is yes. So to look at all situations where the computer says the two best moves differ by only 1/100th of a pawn, in the record of human games and the data that I've taken, the higher move is actually found by players 53 to 55% of the time. In just one game, it might be like, rolling dice, but over thousands of games, the slightly higher value of the move does play out in the sensitivity of the human minds that execute it. And it's quite a regular phenomenon. When the moves are separated by 2/100ths of a pawn, you get almost 60%. You get 58, 59% of the stronger move being preferred by the human player. When it's 3/100ths of a pawn difference, it's over 60%. It's like if you're guessing how many jelly beans there are in a jar, if you get 1,000 people to give estimates, their average will be much closer than what any one person would come up with. Okay? Now, for the final test, if the difference is 0, then with what frequency is the higher move played? 50%? Well, you'd think 50%. Well, it's not the higher move, it's the move that's higher in the table. The move that is listed first by the chess program, breaking ties, the move that the chess program would play. And human players find that move over 57% of the time. Now wait, this is a little bit of a riddle. It's not a typo. So let's think of a concrete case. The famous World Championship match played more than 90 years ago between Jose Capablanca and Alexander Alekhine. My analysis shows over 1,000 cases in those 34 games where the computer program, Stockfish, that I'm using to analyze, said that there were 2 tied equal moves. Now, conditioned on the subset of those positions where those 2 champions played one of those 2 moves, how often did they play the move Stockfish listed higher? In other words, how often did they show that they knew 90 years later which move the computer program Stockfish would prefer? Well, it's like ESP. It's precognition. Now, I'll actually give you the explanation that it comes up at the very end of this talk. Okay, there is a non-parapsychological expectation of why that happens, and it's a very deep reason. And for a very similar reason, between any pair of tied moves, even if they're 6th best and 7th best in a position, I see a very similar split. So what can explain that? Well, I'll come to it. Okay, but there are some other laws that I can give that are more immediate. So one of them, and this is what really set my work apart 10 years ago from other people who didn't notice this, is that humans make what are measured as being larger errors when they are significantly ahead or behind. Okay, now you might reason, well, okay, if they're significantly ahead, they'll play conservative. If they're significantly behind, they'll take risks that the computer can expose, but that maybe their human opponent won't. But in fact, it's a linear progression all the way down to 0. And what it means is that the differences in value of the moves are being perceived in proportion to the value of the position. And what this is actually like, I'll give an analogy to suburban consumerism that's familiar in my country. People really do, even my mother, will drive across town spending all that gas to save $5 on a $20 kitchen gadget. Because look, I got it for $15. I save money. But if you are buying something worth $200, then you don't care so much about $5 when you should. And if you're buying a large appliance costing $2,000, you don't even notice $5,000. Well, apparently we play chess the same way. And I decided that I need to correct for this tendency, which the purple line at the bottom, especially at right, shows that computers do not have, unless they are losing, which means that something else has gone wrong. Okay. So therefore we perceive value, differences in value relative to what is at stake. Now this chart shows something else. The x-axis of this chart is the move number in the game. International chess, uniformly in the world, is played with an initial time budget for 40 moves, 90 minutes or 100 minutes or 2 hours. And if you fail to make 40 moves in that time, you lose the game. But after you make your 40th move, you get a new time budget of a half hour to an hour to use for the rest of the game. So what happens is that people use most of their time budget early and hence are playing the last moves while racing, and they are more prone to make very large mistakes. So this is the actual graph of what happens, and the incidence of error goes down after the 40th move when people can think again. Okay? Well, what actually set Anand apart from other players and was responsible for his initial success 30 years ago is that he played the early part of the game quick and had a lot of time to think about moves in the later stages of the game. In the first match of the recent World Championship, the American ran himself short of time and he was losing. But the fact that he only had seconds left to make the last moves 30 to 40 of the game got his opponent, Carlsen, so excited that Carlsen made a bad move and blundered away his winning position. So the procrastination and bad time budgeting affects also the opponent, and all of that shows up in this graph. And that's a real problem for me because it means that what I am measuring is not so uniform. So in fact, the early moves of any chess game are where people are playing brilliantly, accurately, with small error. And if I redefine the early moves as beginning at move 12 instead of move 9 like I do, then I might make humans look much worse, or I have a different scale. So it's that's a difficult thing. But anyway, I can relate this to a situation where a lot of you have faced time pressure, although with hopefully enough time. That is when you are taking an examination. And especially if it is a multiple choice examination, it is very like playing chess. So here's a famous position, which I will come to again, in the World Championship match 11 years ago, in which V. Anand defeated Vladimir Kramnik to complete the portfolio of being world champion. So white has many choices of move, of which 5 are the most prominent, and in particular option A being to capture a pawn with the knight. And the mathematics of this kind of situation really correspond to the mathematics of analyzing choices and results in taking multiple choice tests. And there's a whole theory of that called item response theory. And in item response theory, you're trying to measure a rating. Well, the rating is the grade on the test, on a 0 to 100 scale or whatever it is. Every test question has a curve that is the likelihood of a person of a certain skill getting the question right. And that is like the likelihood of finding the computer's move. And what item response theory postulates is this is, again, one of our logistic curves. Actually, a curve which allows some separation because the person could guess. So you've always got a 20% chance to get a multiple choice question right if you figuratively flip a coin, guess at random. Okay, so here are various kinds of curves, and the one real difference between them is the slope of the curve. And the slope of the curve is really the discrimination, which is the effect you have of whether you studied or didn't study. So the reward for studying as to how much more likely you will get a particular question right is the discrimination or slope of this curve. So again, the terms are very similar as they are to chess. And that gives the question of whether chess conforms to item response theory. So getting a question right, since the computer is the judge, that means getting the same move the computer played. And indeed, the type of chess cheating that I'm fighting is the same type of cheating as someone who gets 100% on the exam, final exam, after not having gotten anything near on previous exams. How could that happen? There's a second measure, which is how far off incorrect answers are, or how much partial credit a student may deserve for close answers. And that's based on the difference in value between the best move and the move the player selected, which often can be very close. And I scale them down, and the justification for scaling them down was what I said about relative perception of value. So this is the average scale difference metric. So it's the other cheating test and other player quality metric that I follow. And this also gives a utility function for move, namely its move's utility is how close in value to optimal it is. Okay, now I'll go quickly over this. So what item response theory would postulate is that the likelihood of getting a move right should also follow an S-curve in the player's skill, but it really doesn't. It's difficult to test, however, though, because whereas I can give the same exam, same physics exam, to everyone in this room. I can't necessarily give you the same chess position. If you're playing in a tournament, you're going to be playing all different games. If it's a chess position that you all have in common, it's probably one of the very early opening ones where you already know the moves to make because you studied them in a book. Okay? So positions that occur often are already known to most players. It's like having the answers in advance. Tamal and I have debated about whether we could use data on puzzle positions taken by thousands of players, but there are several problems with the data, and its rating distribution was skewed even more heavily than the distribution of players. So we haven't used this. And my cheating test, I can't use puzzle positions at all. I have to use positions that are not book, that the player can't say, oh, I got this move from a book, ones that are unique. Okay. What I have wanted people to do is cluster positions according to similarity of the difference in value mapping. And that leads to an interesting problem about which kind of fall off in value is most treacherous for players. But otherwise, what I use is just my model's own projections for those quantities. So let's look at the data. Yes?
So you're trying to make sure that the person looking at a certain chess position is coming to a decision based on what he feels rather than his training from previous.
Right. It's a question of if the person makes a move that agrees with the computer, I want to judge whether that came from the person's own mind. If it came from a book, then that's that the player read before the game, then that's neither here nor there. So I just don't include it in my test. Okay. Now, so here is the move match projection from the dots are the results using levels from 1600 to 2700. When I began this work almost a decade ago, those were the only values for which I had reliable data. And in fact, when I was showing the logistic curves, you may have noticed the ones on the end were noisier, less definite than the other ones. There's just less data at those levels. So this is the plot I get, and it looks like a great linear fit. The R-squared measure is 99. You can't argue with that. So there's no reason from this range to suspect anything other than the simplest law about the frequency with which players of a given skill agree with computers. But now, taking data from last year, many more games by lower rated players have been archived. And when I add those data points in, now it's clearly not a linear law. Whereas a quadratic law gives a perfect fit. Okay? But if I go to a quadratic law, there are other funny things that happen. Okay, so now I'm just going to flip the axis around. I'm going to make the rating the y-axis instead of the x-axis and make the percentage agreement the x-axis. So I just flipped that around. But I'm going to continue this. Now, by flipping it around, when I put x equal to 100%, that's going to give a rating of perfect agreement with the computer. So what is the rating of perfection? Well, according to a line, it would be, higher, infinity. But a quadratic law rounds over. If I extrapolated it that way, I would get that perfection is 1950 rating, which is an amateur rating. So clearly this makes no sense. What I think this diagram indicates instead is that there is a limitation on the resolving power of the data that I took. I run the computer for a certain amount of time, but that's like running a microscope to a certain degree of resolution. Beyond that, I can't resolve strength or resolve factors. So I believe that the data is actually telling me that my methods peter out at about a 3000 level and about 75% matching to the program. And this sits over a very inconvenient truth for me, which is that the top programs, which are competing with each other, necessarily disagree on moves. That's how one program can beat another. And they disagree with each other about 75%. So I can never catch humans cheating at a higher rate than that. Okay. So I get the introspective conclusion that instead this curve shows a limitation on my data, although it's okay, because I'm judging human players that are significantly below ELO 3000. Okay? And that's enough to divide the human range from the computer range. And for my full test, I use higher quality data that seems to be coherent up to about 100 points higher. Okay, I'll skip over that point. Now let's look at the other score and see if it's a linear or quadratic relationship to value. So here's the same plot, this time of the measured average scale difference in value of move, where the positive value comes from moves that the computer judges to be a mistake, hence the loss in value. And so again, you get a very clear linear relationship, r squared above 0.99, and the higher the rating, the less the error. Okay, higher the rating, less the error, whereas the beginning players make errors at the rate of over a fifth of a pawn per move, losing pawns that rapidly. Now, we could continue this extrapolation, and 0 is about here. So where is the line in terms of rating when it's a 0? Well, you can read that off from the constant term of the regression. And I've gone one place too far. I meant to stay with the line. I must have nicked it. Oops. Okay. Sorry, I'm a little bit lost here. Oh, no. Okay, right, sorry. Okay, so with the linear law, so this is the line, and it looks like a good line except for over here. That postulates a rating of perfection of 3298. But that's very strange because I already told you that computers are over 3300. So it seems to be saying that computers are rated higher than perfection. And that's an issue, even though this looks like a very good linear fit. If I go to a quadratic law, though, even though it makes the line bow out a little more, it does give some more elbow room. Now the rating of perfection is 3462, which is also where my full model places it to be. Okay? So, now, the other thing I could do, though, with the previous data is instead of graphing just the move match percentage, I can actually graph p squared times q. Okay, and then what was quadratic now becomes a nice linear fit again. Okay, but if I do that, then if I want to recover the move match perfection, I have to solve a cubic equation, and the cubic equation has no solution when p is greater than 2/3. So again, that places a ceiling on what my data can solve, and the horizon it gives is even lower than 3000. It's 2860. Okay, so I reject that law, and the question remains, though, what law governs our agreement to computer? Is it a quadratic law or is it linear? So do I really have a non-linearity in my model? And historically, that can be a game changer for scientific modeling. Relativity basically starts off by saying that velocity does not behave linearly. Okay, if you throw a rock from a train that's moving, the velocities don't add. You need the quadratic Lorentz formula to get what happens. Okay? And with the same question about whether a linear or quadratic law is operating for the tendency to make mistakes. Okay? So that's an open question. This is I've discovered this only in the past month, and but I'm going to come to the final part of my talk, is about how we make the model equation and whether we can find a direct indication of depth of thinking instead of merely the subject of error and avoiding blunders. Okay? Now, so what my model is a decision model, and what a decision model does is it predicts the likelihood of an outcome in terms of various factors. If it's an insurance model, it'll predict the likelihood of a disaster in terms of various factors and things in the data. In this case, a decision model, the prime measure it'll use of the frequency of a decision is its utility to the decider. Okay? So a linear model writes that the likelihood is a linear function of the utility. And if utility is relative to optimum, then your base utility is just the alpha part. But probability runs only from 0 to 1. So if you want to compare that with something that's on an open-ended scale, it's mathematically better to compare the logarithm of it. So that created something called the log linear model. And this was a great revelation in decision theory 50 years ago. The multinomial logit model was cited in the Nobel Prize for Daniel McFadden. Okay, so there's a lot of oomph behind this, and you may have heard of this by a different route. When you use a log linear model, you have that the PI, the probability, is the exponential of the utility function. And you get probabilities by normalizing those exponentials, and this operation of exp of utility over the sum of all the possibilities is the softmax operation used in big data all the time. So now question, which law holds in chess? A simple linear model or a log linear model? The answer from my data appears to be neither. Instead, I've wound up going to a log-log linear model, okay? And the equation that I get from that has triple-decker exponentiation. So again, is this a natural law governing human thinking, or is it an unnatural law? Nevertheless, here's the effect. In chess, when I do a log linear model, well, I look at the columns labeled projected percentage and actual percentage. Now I've, on purpose, fitted the numbers on row 1 to agree. That's the statistical fitting procedure that I've used. Row 2, is the model's prediction for the player to play the second best move. And notice that the prediction is about 6 percentage points under what it should be. So I was not expressly fitting for that, but this tells me the model must be wrong if it can be so far off, under projecting the second and third best moves, and actually, by the time you get to the tail, significantly over projecting. Now I worry, this happens in big data all the time, and I don't think that enough skepsis has been used with applications of the log linear model, where people may not have easy ways to test whether the model is really giving true results in other places other than what is expressly being forecast. So one aspect of my chess model is that it has many, many cross-validation methods. Now with the log-log model and the extra exponentiation level, again, I fit it on purpose to make the projection agree with the sample actual. This was, by the way, from a tournament played in London 137 years ago. Okay, but it is also fairly close in the quantities that I did not fit for, the second and third best moves, and the agreement continues to be pretty good as I go down the percentage ranks. And there are many other cross-validations that this model passes. Okay, so now, last topic, and this is the deepest topic of all. Okay, so this is the effect of values as the search progresses. So let's come back to this position. We saw it before, and let's look whether Kramnik, the world champion, should capture that pawn. Now, if you know something about chess, the first thing you'll see is, wait a second, black's queen's protecting it. That would just lose a knight for a pawn, which is giving up 300 to get 100. Not a good deal. So you say no, and the computer agrees with you. At early depths of search, the computer is saying that taking that pawn has a negative value. But then when you play chess, you begin to look a little further ahead. And you see, well, look, if black takes the knight with the queen is on an exposed square. I can then attack it with my rook, and that rook is lining up the queen with the knight. Okay. And when you see that, the move begins to look better. And in fact, at depth 9, the Stockfish program thinks capturing the pawn is the best move in the position. Now, there are a few things, the other things you have to think about. Black can counterattack against your queen, you take, and eventually get the bishop. And Kramnik had in his mind this position with black's knight still here, and said, coast is clear, I'm ahead half a pawn, went ahead and played the move. But Anand had seen deeper, and in this position, with Kramnik still unaware, uncorked this sacrificial knight move and take to the pawn. But black will take back with his pawn, and white's rook is powerless to prevent black's pawn from marching forward to checkmate white's king. And in this position, Kramnik gave up. And the computer sees this at depth 15. The computer sees what Anand came up with. The value of the move swings from plus 51 to minus 181. So this is a move that swings down. It's the chess analog of a googly at cricket, where you don't get to the pitch and it comes and hits your stump. And so this is a notion of swing. Also notice that what the computer finally decides are the two best moves are tied in value. Okay, so a move that initially looks best but whose value swings down on deeper reflection is a powerful trap. In this case, a world champion level trap. Okay, and note also that two moves are tied for equal top value. Okay, and if we went back to look at that chart, we would see that the second best move, the second row, the move has a minus value more often than the first move. So it was inferior for a longer part of the time. So this was the discovery that Tamal made in his thesis that was more powerful than I had imagined it, which is that this swing in value actually affects the human mind. So the combination of this and stable sorting means that, first of all, in the teaser cases that I had before, the second best move, even though it was tied optimal at the end, was perceived as inferior by both the computer and the human subject for a longer time, and hence looks less attractive to the human player, and hence only the 43% likelihood of choosing it versus 57-58% for the first listed move. So that's the non-ESP, non-parapsychology explanation of that phenomenon. Okay, and what Tamal did is a measure that proved that it matters much more than I expected, that in some cases it should change my forecast from 30% to 70%. So I had to take notice of this. And another result is that the depth at which your mistakes are exposed grows linearly with your skill rating. So better players commit deeper errors. You can understand it that way. But it also means that in chess, we can get an estimate of your ability by looking only at the positions where you screwed up. Not at your good moves, but by the depth of your mistakes. So we introduced a model parameter to handle this. These are my last two slides. And what goes with this, what the model parameter is trying to catch is your depth of thinking, and not what you decide, but when and why do you decide to stop thinking and convert the thought into action. And so what the parameter is measuring is the tendency to act prematurely, as Kramnik did by capturing the fateful pawn with his knight. Okay, so we add a term for h to the utility function. And by dividing both terms by my sensitivity parameter, what happens is it's like a balance. If h is bigger than 1, the right-hand scale tips down. If h is less than 1, the left-hand scale, the objective measure of value, is the one that carries greater weight. So what happens in chess? Well, so which one wins? Well, we're human, right? So do we care about subjective immediate value or objective value? Well, I have to confess it's not clear. When I fit the way I want to fit, I get h greater than 1.5. And this destabilizes my model completely. Whereas if I fit by maximum likely estimation, I get h less than 0.5, but MLE gives wrong values. It does not give the agreement in the top row that I need from those charts. So it compounds all the problems of my cross-checks. And whereas fitting the equations with the h parameter too often gives near perfect cross-checks, but it also creates a badly behaved nonlinear model. Okay, and even when it works, it's like if a moon has come into our solar system, it might throw off the other planets, and I get instability in my model. Okay, and bad linear performance. So finally, what can we conclude from all of this investigation? We have seen some laws that govern human thought, logistic curve laws governing expectations, relative perception of value, time management failings, which complicate my modeling task too, the agreement with the computer. Does that vary linear with rating, or is there a nonlinear law governing? And then finally, the question of value swings and decision stopping time. How should we best model? I'm currently at a state where I don't know how to model it best. Well, predictive analytic models govern all of us in our walks of life today, and they're supposed to handle factors like this. But what this points out is the need to scrutinize one's modeling. A good model has to be upkept like a car to keep it in tune. And there are indications that for all its success and application, my chess model is out of tune. Okay. And one needs also to be skeptical of the data to know its validity range, where it might peter out and lose its force. Well, the model that I'm deploying now is conservative fallback settings. So to a large extent, this is an issue with how Tamal and I have wanted to extend it. Hopefully, continued research and trials will give brighter light and also sharper guidance for our own scientific and mental fitness. Okay, thank you very much for... I don't know if I've left time for questions, but I'll be happy to take some.